number was like 10 or 20. It was a very small group, wasn't it, in the beginning?
There were about 50 in IETF.
Okay, but mainly here, not here, but on the West Coast area, I think.
No, on the East Coast.
East Coast. Oh.
That one was at BBN.
Oh, okay. Yeah, I think from
Norm.
I just told Stuart, we just got that data stuff up.
So, Cisco is kicking me out for the second time now.
I thought so. Did you get? Was that August? Or?
They kicked me out a year ago,
Right. Okay.
February. But at the same time, they asked me to stay on part-time with a contract and do chair advice and some research stuff and all that. But that contract went for a year and a half. Maybe 3 months. 3 months of quarter.
Well, a lot of us are joining the board. Resistance is futile.
That's what we used to say about Cisco.
Yeah, I know. That's what it's an engineering company.
I think we can start.
Oh, is it
9 o'clock?
Don't be shy. Could everybody get seated, please? We're going to start. That includes you too, Karini. Yeah, just say you're going to pass the blue sheets and then get into.
Okay, so let's start. So welcome to the Mpls session. I think first thing we want to do, we have a couple of words from our area director, and I will just distribute the blue sheets in between.
Good morning, everybody. I'm Deborah, if you don't know me. We have a very special occasion today. This marks George Swallow's 20th year anniversary for having the Mpls working group and the Mpls working group. And it's his 61st meeting. Well, it's yours too, right? No. Oh, you came before.
Yeah.
Okay, so you got the message. Thank you.
Yeah, in fact, I mean, my first meeting was IETF number 43 in Orlando in '98, and I think at that time George was already working group chair of the Mpls working group. So I think he did a very good job during the last 20 years.
So you're going to pass the blue sheets around?
Yeah, blue sheets are already on its way. So I think we can
go ahead.
Yeah. So note well statement. And so then we basically start with a working group meeting. So administrative stuff, so blue sheets, I think, are circling around. Data tracker, here are all information, bless you, on the Mpls working group. Minutes, who's taking minutes? You're taking minutes. Meet Echo, I think it's also online and up and running. And all the information, slides and so on are already uploaded to the Mpls web page. So.
So we have the agenda is before you. If anybody has any comments or suggestions about it, please speak now or forever hold your peace. And then this is the agenda for Friday, which is a joint meeting with CCAMP, PCE, and TEAS. So, and that's to discuss Yang models. So, as Lou said, sorry to have you divided between the beginning and end of the week, but we don't have control over the powers that be. And so the working group status, we have one new RFC that's RD 8029, which is the BIS document for RFC 4279, which is LSP ping. And this is the document status. You can find all this information on the URL that was on a couple slides back on the work group. But calling your attention, we have seven out of the now 19 listed there are with the RFC editor or in the process of getting to the RFC editor through the ISG. When the slides were first put together, there were 20, but opportunistic encryption expired, so it's not on the list anymore. But we'll have a word about that later. So there are a number of workgroup documents. These are documents that are not Mpls workgroup documents, but they're workgroup documents going on in other workgroups that are related to Mpls. And just in case you're not aware, there's about 150 RFCs that have come out of this workgroup, but in total there are, I think I counted 747 RFCs that reference or came out of here in total. So if you want to read the whole document set, you know, plan some time. And then there are two others that are individual drafts that we should be paying attention to as well. We got a number of new IDs into this meeting, and they will all be presented except for, do you have that one? There's one new ID that is not being presented because I'm not sure if it's travel or they just don't feel that it's quite ready to be presented. But otherwise, we'll have all those in the agenda. The updated drafts, synonymous flow labels, framework, the authors met yesterday to discuss how to progress the whole document set, and we weren't prepared to carry that forth on this meeting, so we'll have updated documents for the next meeting. And nothing else I want to say there. So in progress, opportunistic encryption. There's a little bit of cleanup work that the authors want to do. Adrian had gone around. Well, who's the other author on that? Stephen had gone around and gotten people to start to implement it at some universities. Unfortunately, the graduate students graduated before they finished it, and so they will refresh the draft, and Adrian considers it a good candidate for an open source project if anybody cares to take that on. So yeah, there are a number of drafts that are in expert review, and the chairs need to chase down one of them has been there at an obscenely long time, but like half a year, so I have to figure out what's going on there. And that's any issues there. Um, there is some confusion as to whether Carlos is joining this draft or not. Somebody told Noah that he is, but his name isn't on it yet. So, anyway, he's there. Carlos is involved, and you know, hopefully this will keep moving along smoothly. Bidirectional forwarding detection, directed return path. We had a last call. It did not get through the last call because of an IPR issue. Since then, the authors have revised the document, and in their opinion, they've removed that dependency. However, the Erickson lawyers either don't agree with that assessment or are otherwise afraid to remove that IPR, or I don't know what their motive is. But the IPR statement remains, and we will have another last call, and all I can do is present you those facts, and you know, the working group can make what decision it makes. But we'll have that last call very shortly after this meeting. And that is it. We are ready for our first presentation. So, Kariti, RMR.
Okay, all right, thanks. Okay, so this is a quick update. Not a whole lot of stuff has changed in this. 94, that's good. Okay, I'm a few centuries behind. Yeah, I took those slides and updated some of it, not all of it. It's getting fixed in real time. This is really cool. Okay, so, and actually my co-author is here. Oh, he was here. There he is, yes. Okay, so one of the things as we started implementing this, so we do have kind of a very initial version of the implementation, some of the ISI stuff, and we started looking at RSVP and LDP for the signaling. And we found that there is this question that we kind of answered that it should be a full ring, but in the implementation we ran into a few issues. The other thing is, if you have not a full ring but a half ring, should RMR address that? And if RMR does address that, how would it address that? And then, of course, is there anything else? So RMR basically says we want to build a ring LSP. So you start and end at the same place. Well, if you do that with RSVP, there are lots of checks in RSVP that a path message doesn't go back through or to the source, the ingress. And in our code, we have all these tests. You know, as the path message is going along the LSP, you test, am I the ingress? So it's not a big thing, but there is a lot of it. So we sort of came back to the question: should the LSP start and end at the node that it, at the same node, or should it start at the next node and end at the previous node, kind of thing? So from an aesthetic point of view, it is nice for the LSP to start and end at the same node. It makes it much easier from many points of view. For example, when you think the ring has been fully discovered, you just kick off the path message, and you know it goes around, comes back to you, and it's done. But if not, you have to tell your neighbor, hey, kick off the path message, or the neighbor has to decide he wants to kick off the path message, which is going to end at you. So if we can get past all the loop checks, we'd much rather do it that way. So our inclination is to keep it the way it currently is, but the question to the working group is that the right approach? So if you think about it here, you have an LSP starting and ending at 1. So the green LSP is how we are envisioning it right now. An alternative is the LSP that's going in the clockwise direction that ends at 1 starts at 2, and the LSP that's going in the anti-clockwise direction that ends at 1 starts at 0. It's not really nice to do it that way. And so again, as we go through the next stage of implementation, if the green LSP works, I'd much rather do it that way. The other advantage is that you can do a self-ping of the LSP, but you're literally checking the entire LSP. So you're at 1, and 1 will never put real traffic into the LSP, but by putting an LSP ping packet or a BFD packet into the LSP and seeing that it comes back to itself, it can say, this LSP is working. Every hop is doing the right thing. So it's nice to have this end-to-end test of the LSP. So for those
Can I
reasons,
make a comment?
yeah, sure.
It doesn't guarantee that everything's working right, because some of the things are supposed to drop off, aren't they? I mean, everything comes back to that.
Yes.
Yeah. Okay.
So
Sorry.
the goal is to get to 1.
Yeah.
And so, 2 can get to 1, 3 can get to 1, but if 1 can get to 1, everyone can get to 1.
So the worst you could have is somehow a label got corrupted in a forwarding table, and it wasn't going on to that LSP.
Right. So if the hop from 1 to 2 broke, one might think the LSP is broken, but that's not, it's not really. But if it works, everything is working. If it is broken, if it's that first hop, then you don't want to see that.
So I'm just making the point that doesn't prove it. Unless you ping from 2, you don't know for sure that 2 can forward on to that LSP.
Oh, okay.
That's a very rare case.
Yes, understood. So yes, every node could in principle be an ingress, and so you don't know that node's ingress, push the label and send it to 1 is working. But in general, you know that all the cross connects are working if 1 pings itself. Oh, okay. Oh, I had all this. Okay, now you can read it. So if you want to do the end-to-end OAM, it works nicely with this. Half rings are if I don't have that connection between, and it's not a half ring, but there are people who call this a half ring. It's a not full ring. So if I don't have the connection between a link between 0 and 1, so why would you do this? I don't know. But some people consider that a wasted interface because, stuff that I'm sending from 0 to here, I'll just send this way. Stuff that I'm sending there, I'll send that way. But I'll probably never send stuff from 0 to 2, so why put an interface there? I mean, people do this, and in talking to people about RMR, I've seen these in their networks. And so the question is, how do we handle this with RMR? Or is this a situation we want to handle with RMR? One solution is that you create a pseudo wire going from 0 to 1 and finish the ring, but with a pseudo wire. And then you use that only when you have a protection scenario. And there are a few other things, but this is something that we're considering. And the question that for the working group is this a scenario that falls under the purview of RMR, or should there be a different way of solving this? So any suggestions are welcome. So we've done a lot of thinking about this. We've also considered should we do anything with multicast on the ring? And my initial thought was use the sonnet type drop and continue. But talking to people who actually know multicast better than I do, including Mpls multicast, they said we don't need to do anything special. It's just another topology. So at this point, we're not going to pursue anything with multicast. But if you guys have any thoughts, any questions, I'm not going to quite do a working group last call request at this IETF. I do want to get a little further with the implementation, and if any things come up, we want to address that. But we think that we're getting really close, and so we want to, think about getting to our last call. There is a companion document about the ISIS and OSPF extensions, which should be in that working group. I haven't actually put it on their agenda. And then there are a couple of documents showing how signaling in LDP and RSVP would work with RMR.
So, other folks are presenting those, right?
Yeah.
Okay.
Yeah. So if you have questions, or I'll move on.
Any questions? I guess they've heard you enough times now. Thank you.
Yes.
We got a question. No? Oh, okay. So we now have RSVP extensions for RMR. So we continue with RMR for a couple more presentations yet.
Okay. Good morning, everyone. My name is Abhishek Deshmukh. I'll be presenting signaling extensions for resident Mpls rings. So I'll start with RSVP extensions, and then I'll move with the LDP extensions. So as Kitty described, the ring LSP forms a loop. It goes back from the same node, so the ingress and egress are the same node for the ring LSP. And also the ring LSP is a multi-point two-point LSP. So that means each transit node will also add an ingress route for that particular LSP. So if you see here in the next slide, the LSP, once the IGP discovery of the ring is complete, each node in the ring will signal an LSP to itself. For example, one will signal an LSP to itself, and each node will follow. And so we'll have two LSPs, one in clockwise and one in anti-clockwise direction. The reason for that is the protection route will be the LSP going in the reverse direction. So there is no link protection or node protection required. And so as the LSP is going across the ring, we have the so when the LSP path message reaches 2 will also when the ResV comes back to 2 will also install a transit route as well as an ingress route for that particular LSP. And one more thing is the ring will have, so when all of the nodes signal their corresponding ring LSPs, there will be 2n ring LSPs, not n square LSPs. So this slide talks about the extensions to RSVP. So we have a new session object defined for this purpose. The first field is the anchor node address. So that is the address of the LSP which is originating, which is the same node. So this differs from the plain vanilla RSVP implementation that we have the destination address there. So this we don't need it anymore. And then the ring flags define the direction of that particular LSP, whether it is clockwise or anti-clockwise. And we have this, instead of tunnel ID, we have this new field called MBB ID, which will ensure that whenever there are some changes, let's say some node goes away in the ring, let's say node 3 goes away in this ring, and we have to still signal the new ring, then in that case, we'll just signal a new MBB ID in that case, and the ring ID remains constant. So in this case, the ring ID is 17. And for the sender template object, there are not really changes in any format, but semantics of the sender template object slightly change. So what we'll do is as the path message is going across the ring, we'll have each node will add its own sender template on the incoming path message. So the reason behind this is that this is going to be a multi-point to point LSP, as we described earlier. So whenever, let's say, the link between 3 and 4 goes down, still we have to maintain the LSP is going from 4 to back to 1. So for doing that, we are adding this extra. Each node is adding its own sender template in the outgoing, and the corresponding resume message will also have its own filter spec and flow spec objects. And then bandwidth management. So the one interesting thing about ring is we'll have so bandwidth can change hop by hop. So for this LSP going across the ring from 1, originated from 1, the bandwidth can change at 5. 5 can request a different bandwidth. 6 can request a different bandwidth. You have a question?
Yes, Greg Mirsky, ZT. Can we go to the previous slide, please? Okay, so you collect the sender templates in one object in a path message. So that seems that it limits your size of the ring in number of nodes that you can support.
That is because of the fragmentation you're talking about?
Yes.
Okay. So we thought about the fragmentation issue, but so one alternative is we can have different path messages with different sender templates. So for example, each node will have a different path message with a different sender. Instead of combining everything in one path message, you can have like multiple path messages.
But then how you do the association by their LSP ID?
Right. No, by the ring ID. We have this ring ID here.
So
in the session, object will.
But then you need to define. So basically, effectively, you're saying you can have multiple path messages for the same LSP. I don't think it's a real practice.
In case of P2MP, we do that, right? Anyway, so you can have P2MP, different S2Ls can have different path messages, and then you can have either just a single path message, or you can have so the standard defines both of them. You can have combined path message, or you can have individual path messages. And even if you have individual path messages, still.
But how you identify? Because if something changes in one of the path messages, for example, you withdraw the node. So how you identify the particular path messages? You have to reflood all path messages?
So the path message is going across the ring, right? So anyway, so withdraw as in you will send part tier or something to withdraw it, or.
But you will need to resend all the path messages, because you cannot really, you don't identify the particular path message, because you use the set of path messages to describe NP to P.
Right.
Okay, so if anything changes, you have to reflood all the path messages.
So each node will be responsible for its own path message, right? Because this is that path message is really associated with the LSP, which is originating from some other node. So let's say node 1 decides it no longer wants to signal that LSP. Then node 1 will send a part tier, and when node 3 receives that, node 3 will also generate its own part tier for that particular LSP.
But they use the same ring ID.
Can I jump in?
Yeah, sure.
Kiriti here. I mean, we could use multiple path messages. We could just use IP fragmentation. But I think if you do the math, unless you have a really small MPU, you can go many hops before this becomes a real issue. So I think what Abhishek is saying is you could do these different things, but these are sort of backup, alternative things. You really, we'd prefer to just send one path message with multiple sender templates. And I haven't done the math, but I think you can do quite a lot of hops before you really run out of stuff and start doing fragmentation.
Yeah, I just, in one of the discussions with the CCAMP RSVP, it was pointed out that MTU size does matter, and you have to really consider the situation and discuss it. I'm just, again, I don't want us to debate it any longer, but I just want to point that it's an area thing that you need to
Okay.
consider.
Sure.
Okay.
Yeah, so about bandwidth management stuff. As I was saying, the LSP originated from one, for that LSP, each transit node can decide it wants, so for, let's say, the node 5 wants a bandwidth, some service come up, and node 5 wants increased bandwidth for the segment going from 5 to 1. And also node 6 also wants to increase bandwidth for the segment going from 6 to 1. So in that case, we'll have another, like as I was describing in previous slide, we'll just add a new sender template object for that particular segment. So this slide explains that in further detail. So here in this case, node 5 is are trying to increase the bandwidth. All the first 4 sender templates are same, and there's no change. But in node 5 and node 5, it signals a new LSP ID for that particular segment going from 5 to 1, and it also have a corresponding tspec object. And the resume message, when it comes back, it will have the corresponding flow spec and filter spec objects. So this slide just explains various scenarios. So let's say there is not sufficient bandwidth available at node 9 for this particular LSP ID, then it will just send out a path error for that particular LSP ID sender template combination. If the bandwidth management if the bandwidth utilization is, so each node will have its own like bandwidth accounting depending on the whatever bandwidth is requested, and if there is sufficient bandwidth available, then it will receive just one resume message with the corresponding tspec and flow spec objects. Flow spec and filter spec objects. So that is it. And one more thing about the reservation style. So this will be a shared explicit reservation style, but the shared explicit means the reservation will be shared between the corresponding senders. So in this case, for the LSP originating from sender template 5, we will share the bandwidth. So LSP ID 2 and 3 will share that bandwidth when it is being set up. After that, the LSP ID 2 will be teared down. So as next steps, we need more feedback from the working group, and we request for the working group adoption.
My name is Art.
Yeah, go to the mic, and they can't hear you on Meet Echo at all.
Tarek Saad from Cisco. I saw you introducing MBB ID.
Right.
You have Ring ID and you have LSP ID.
Mhm.
And unless I missed, you didn't describe how you're using MBB ID and why do we need three IDs?
So Ring ID is constant, so it never changes. Ring ID is something similar to the extended tunnel ID that we have in the current path message. For this particular ring, the ring ID is 17. So this will never change. So this just ensures that, so there can be multiple intersecting rings across, right? So for example, this is node 3 and 4. There can be another ring which is sharing node 3 and 4, and that ring ID might be something else like 18 or 19. So so for node 3 to distinguish between different rings, that ring ID is needed. And the MBB ID will be used when we are when we are signaling a new session, it's kind of a different tunnel ID. You can't really say it as a MBB concept. So let's say we want to signal.
I'm not clear what's the difference between ring and a tunnel. So because you're saying there is a ring ID and a tunnel ID, and
No, I'm saying the MBB ID is corresponding to the tunnel ID that we have right now in RSVP. So, for example, this link when this node 3 goes away, and we have to just signal the ring across 1, 2, and then the next stop is 4. Then in that case, node 1 wants to signal a new instance of that particular ring LSP. So that will then in that case it will signal with the new ID.
okay, it's not perfectly clear to me. Like for example, one ring can have many tunnels, right? Is that what you're saying?
One ring can no. So
No. Okay, so then
Yeah.
one ID can.
right. So the ring, right? So whenever the path message goes across the ring, so in that case, each node will have its own, will add its own path message. But the tunnels that you are saying, the MBB ID that was there, so that will be only used when you are moving away from some node, or there's some new instance you are signaling.
Okay.
For the LSP.
So we can discuss it offline, but I have very strong objections to putting that in the session object rather than the sender object, as the LSP ID is what is used today for all the other FRRs,
Right.
MBB kind of things.
Okay.
So
So the LSP ID will be, so we are using it in the sender template object that you are talking about, right?
well,
So
you can create a new sender template object as well. So.
Yeah. So currently we are using it for a different purpose for the bandwidth management.
What I'm saying is you can define a new C type. Is that the right word? It's yeah.
Okay. Yeah, we'll consider that one.
Any other questions? Thank you.
So about the working group document, so we want this to be for the working group adoption.
So it being a first time draft, how many people have read the draft? And well, just based on the number of people who read it, I think that we need a little more review. And now that people have heard your presentation, then
Okay.
you have a chance to better understand it going into reading it. We'll hold off on that until next meeting.
Okay.
Okay.
So the next will be LDP extensions. So the author for this is my colleague Santosh. So I'll be presenting it on his behalf. So this slide explains what are the issues with LDP on the ring. As you know, with the ring topology, we don't really have any LFA production possible. It will be very difficult to have LFA. And also LDP or RSVP also has similar problems when we are doing the standard FRR. And also the SPF also. So let's say we don't have any production in that case. When the LSP is going back, in that case, we'll have many micro loops. So the LDP LSPs, similar to RSVP, we have two LSPs, counter-rotating LSPs across the ring. And those will be signaled from the egress towards itself. And once the signaling is complete, we'll have each node will add the ingress as well as standard route. It's same as the RSVP concept. So the protection is natural, like we don't have no need for any LFA or RSVP bypasses. We just use the other side LSPs as the protection LSP. So the protection protocol extensions needed for these are we'll have the new RMR capability object in the LDP initialization message. Will signal that to find out what nodes are capable of ring signaling across the entire ring. And once we have all the nodes identified, we'll have the label mapping message with the FEC element to support to signal this counter-rotating LSPs. And that object will also have these ring flags and ring IDs. So all those details are mentioned in the draft. And once this LSPs are established, we have the corresponding routes and everything installed. So the next steps are like we need more feedback on this draft also from the working group, and we request for the working group adoption for this draft as well.
So this question may be for Kriti as much as you. Why do we need to extend both protocols? And
Well, so for LDP, you don't want to use the usual way of finding your upstream, because you want to go clockwise or counterclockwise depending on which way you're going. So you need an extension that says.
I'm not asking why you need the extension.
Yeah.
I'm asking why you want to be able to set these up with two different protocols.
Oh. It's up to people who, if you deploy LDP in your network and you're more comfortable with LDP, you do it with LDP. If you're more comfortable with RSVP, you do it with RSVP.
I think people who are comfortable with RSVP will use rings, and people who are not comfortable with RSVP probably won't use rings anyway if you do it in LDP.
Well, the fact is that you have rings, right?
Okay.
So the rings are independent.
Yeah.
What
Anyway.
you're comfortable with signaling is.
Right. But when we do a work group adoption, I will ask the room whether we consider that we need two protocols or we can live with just one.
So for the discovery, I'm doing both ISIS and OSPF. I'm not going to mandate someone you have to switch to ISIS. They should. That's a whole separate thing. But I'm not going to mandate that they switch the IGP just because they're running on a ring. And so I think it's the same thing. But sure, ask the question to the working group.
But there was an attempt to extend LDP to do tunnels, and that.
You're talking about CRLDP.
Yeah.
Yeah, this is not about CRLDP.
Well, it brings back memories.
Real quick, George, Eric Osborne, level 3. Is this thing? I guess it is on. I could see a need where some people are going to want to do this with RSVP and some with LDP. I don't have a specific use case. I haven't dug into it a lot, but if it can be done in both, it's going to make people's choices a lot easier. Is my second opinion. That helps.
Any other questions?
Hi, my name is Harish Sitaraman. So I'm presenting this draft on behalf of the co-authors. Basically introduces RSVP signaling on top of a shared Mpls forwarding plane. So the basic motivation of this was to couple RSVP signaling plane on top of the segment routing type of Mpls forwarding plane, using the similarity would be similar to adjacency SIDs. It also decouples any platform limitations that one may have on fib sizes. So fibs that are very small can also operate. RSVP can run on that, thereby managing the data plane footprint that's available on the box. In the past IETFs, I think there have been working group documents that have been adopted to scale the control plane in RSVP as such. So this document is more leaning on the data plane side, and to be able to run RSVP on top of such a lean data plane. So what benefits do we get in addition to what RSVP already gives? So in the first way, we have a transit label on a TE link that's basically shared across any LSP. So regardless of where the LSP starts from and where it ends, as long as it transits a certain link, any LSP can share that label. And the forwarding plane state on any given LSR is approximately the number of neighbors on that LSR. So the data plane footprint is roughly that number of interfaces or the neighbors on that box. The tunnel setup time is also reduced because we don't program the forwarding plane during the LSP setup. So traditionally in RSVP, when you set up the LSP, you allocate a label, you program the hard forwarding plane. Similarly, when you delete an LSP, you have to delete that state. So none of that will happen. Instead, all of these are pre-installed labels in the forwarding plane. And you can share labels across make before breaks. So today, by procedures, make before break, would have to we signal a brand new LSP with a higher LSP ID, allocate new labels, and you have to delete the old one. So here, pretty much, if the paths actually overlap due to something like auto bandwidth or some applications that perform make before break that have path overlaps, you can pretty much share all the labels along the path, and there's no change to any routes at the head end either. And lastly, but not least, all the control plane features that RSVP has have been well known. Fast reroute, admission control, preemption, auto bandwidth applications, all of them just continue to work unchanged. So we introduced this concept called pop and forward label. So pop and forward is basically an existing label operation. It's already done. For example, at a penultimate hop router, you would pretty much see incoming label getting popped and forwarded down an interface. So the semantic is rather common. An LSR should allocate such a label for an interface or a TE link when it actually discovers that a neighbor or when it adds the TE link, and it installs the label route in the fib. And the forwarding action is basically to pop the label should it receive a packet with that label and send it across that to that neighbor. Additional labels will be required for protection scenarios. Primarily for link protection, you would need one additional label on that interface per interface. So this happens at the start, and it's all pre-installed in the system. So this gives an example of what actually happens at the signaling level. So just shows two tunnels at the top, T1 and T2, and one goes from A to E, and the path is shown on the slides, and the other one go from F to E. In both these situations, both these tunnels actually have the same label stack. So a point that I guess brings about here is once the ingress actually imposes a label stack at this point in time, and both these tunnels have the same label stack. They share the links, the red colored links, and on their paths, and they share the same labels that those links offer. In terms of the signaling extensions, actually rather very minimal. There's the LSP attributes object or the required attributes object in the path message that's already available. It basically introduces another flag in there for pop label, so the ingress can actually signal the LSP asking for this type of a tunnel. And similarly, on the reverse direction, when the RSV comes back, there is a bit that's flag actually in the RRO label subobject that basically indicates that a given label is a pop label or traditional swap label. So when the ingress actually receives all these labels recorded in the RRO, it can basically construct the entire stack out of the RRO and can install that. It also allows an ability to do explicit delegation of label stacks. So explicit or automatic delegation. So in this example, actually, let's say for some reason the LSP length is very long and you're unable to impose the entire stack on the ingress. Either you can explicitly ask the ingress to pick one or more hops along the way. The ingress could do that by itself, or an operator could decide which hops should be an explicit delegation hops. In the automatic case, the ingress can pretty much manage this by itself. There would be no intervention at all. And in this example, actually, D and G are delegation points, and the labels in red there are actually traditional swap labels. So they are not the defined pop labels from this document. So if you look at the stack at A, when the packet actually does a pop and forward, B pops 100, C pops 300, and the packet gets to D, it's 350. That's a traditional type of a swap delegation label. So it in turn imposes the labels for the next 3 hops, and G imposes the remaining 2 hops. So how many delegation points you have to pick and who picks them can all be automated. So depending on the length of the LSP. And to actually, for the ingress to indicate who the delegation points are, it can actually have, there's an existing hop attributes sub-object. There's an attribute TLV that we can introduce in there that can per ERO, it can actually, per hop, it can actually tell who the delegation point is.
Hi, Greg Mirsky, ZT. So I just wonder, why need to introduce new construct when you effectively can do the stitching of this segment LSPs and use everything that's already available?
You mean in RSVP?
Yeah, you can basically, what you're doing is that you're creating 3 different segment tunnels, and you stitch them.
This is actually not precisely stitching per se, right? This is more of hop management in various ways. It's a delicate.
No, but again, you can just call it differently, but you effectively stitching. You say that I cannot impose more than certain number of labels because of some limitations, and I want, once there is enough space to stick more labels, add them later. So you effectively.
So the platform of A can actually push the entire label stack. It can push it. So this is just an option in case.
In my view, you just introduce new construct for not good enough reason.
So if you're going to use stitching, don't you need some control logic to be on the stitching points? Explicit control logic.
Yeah, but we do stitching
But here
for many years.
Right, but here
No, but again, it's about use what we have or add some new construct.
you're minimizing the number of touch points.
Speaking as an individual, I think stitching is pretty hard to manage compared to just setting it up in one session. So
you also lose end-to-end visibility in stitching. So
Yeah, so Kiriti, I want to emphasize that last point. In the control plane, there's a single path message from A to J.
Okay.
So it is one LSP. In the data plane, what happens, don't let that confuse you. There's one LSP here. It's not three LSP.
So, so another thing is this also you're also able to mix like different types of labels. So, for instance, if you take D and G and let's say they don't support this feature at all, and it's traditional RSVP running there, allocating regular swap labels on that hop. The local logic is only on the ingress. The ingress knows what type of label each hop provides. It can actually construct the stack by itself. So this is just an example, just to show that the logic is just housed on the ingress. It just needs to look at what labels come from which hop and construct the stack appropriately. And the facility backup link protection just works like it does today. So in this example, it just shows an example at B, where there's a link protecting facility backup. You would traditionally pop the label 151 and then you push it down the BC link. In this case, you would pop 151 and push it down the bypass, and C would still receive the same packet. So this still continues to work. So with respect to next steps, we request working group feedback. We update the draft with some of this feedback and also have prototype, just one updated based on some experience. The automatic delegation part that I talked about isn't yet there in the draft. It's have to be updated. The draft talks about explicit delegation. And node protection we have solution for all of this. We ran out of time before the submission deadline to update the sections.
Okay. I have two comments. One is Chair. Thank you for submitting a very well-written first draft. I wish more of the drafts that came in at 00 were of this quality. And my second comment, as an individual, I enthusiastically support the work.
Thanks.
Any questions? Okay, thank you.
Okay, so you've seen this draft before. It's basically fast readout for LDP, but node protection. And we're going to use RSVP signaled LSPs to do the node protection. So the main thing here is that if you're looking at node protection for RSVP, for LDP, there have been many solutions provided. So you can use SR, you can use TI-LFA, and there are many types of LFA for this. What we're saying here is that you can do link and node protection using RSVP-TE. So independent of the topology, if you can signal the path, you can use SRLGs. You can find an alternate path that is sort of independent and then use that for protection. So the configuration that you need for this is really small. I think we've gone through much of this, so we're using existing mechanisms. We're not inventing any new mechanisms. All we're saying is you have RSVPT, you've got LDP, you've got targeted LDP sessions, which you need for node protection. Just use those, put them together to show how to protect LDP tunnels. This avoids having complex computations and that depend very much on the topology. I'm really confused by the slide. I'm just the presenter, don't shoot me. I think it applies to SR, but it says yes and no. So if someone can explain that to me, I'll be very happy. I would have just said yes. But the solution, the object is to provide protection. And so you can create this bypass tunnel with RSVP-TE. And if you're using node SIDs, you would need something like that because you're otherwise dependent on the IGP. So link protection is already deployed, but we're saying you can do it for node protection as well. So this has been approached by many others in different ways. We think that the procedures here are much simpler. We're using existing mechanisms. And if you're not just allergic to RSVP-TE, this works quite nicely. So I guess at this point, we've addressed a lot of the questions. The draft has been pretty stable. We have implementations. So the authors would like to request a working group document status, adoption by some working group. We did get the feedback last time that we should present this in RTGWG, so we'll do that. And we're hoping that one of these working groups, having decided which will own this, will take this to working group status. Comments, questions? Okay, thank you.
Thank you. Yingman? Oh, it's remote.
Yeah, not online.
No participants queued up to present. So we will move along to the next one. And if I try to pronounce your name, I'm going to slaughter it. So this is the unified source presentation.
I think that's it. Coming in from the tech group. Yeah. Okay.
You can't pronounce it, Brian.
How do I got it? I start or?
How do I recognize it?
Just press the button. Yeah.
You got the mic.
Okay. Right, good morning.
No,
Wrong one.
not you. Sorry. Tavik, are you there? It's human.
Hello, can you hear me?
Yes, we can hear you.
Hello, can you hear me?
Yes, we can hear you.
Okay, okay, thank you.
I have to take my hand off the button.
Yep.
We lost him. Stuart? Yes, so we will let you present, and as soon as he's got his technical problems resolved, then we'll get that.
Okay, so Stuart, right. So this is a follow-on from a piece of work I spoke about at the last IETF, extending the theme a bit. So next slide, please. Right. Oh, I can do that myself, can I? Which button do I press? The right and the left button. Right. So these are the goals that we had for this this study. We wanted to carry MPLS segment routing packets across network segments that do not support MPLS. Okay, so this is a bridging across an IP gap in the network, as it were, or MPLS gap in the network. We wanted to provide segment routing in IPv4 and IPv6 networks. Another goal was to try and find a minimalist approach to service function chaining. We wanted to use existing hardware and IETF specifications wherever possible. And we wanted to provide a common approach from all of the for all of the above, if we could do that. And we also have set ourselves as a requirement that we should be able to do this without using any of the pure MPLS control plane items. So SDN or segment routing extensions in the IGPs, but not a full-blown sort of LDP or SVP implementation, unless that's actually what people wanted to use. So here's what the company encapsulation looks like. We start off with an IP header. Of course, we have MAC headers in front of that. Start with an IP header. You may, for ECMP reasons, then follow this with a UDP header. And then we have an MPLS label stack, and then we have the payload. Now, payload is clearly outside the scope of this discussion. The key part of the MPLS label stack is to remember that it is a hardware-friendly way of carrying 20-bit SIDs or 20-bit instructions. Just think about that as not as a pure MPLS implementation, just a very, very convenient, very hardware-friendly way of carrying the instructions as to what to do with the packet when you take the outer IP layer away. UDP, because that's the most backwards compatible way of doing ECMP in this system. We can't use the ELIs or anything because devices on the path wouldn't know how to do that. But they're all good at doing the 5-tuple. So UDP is the right way of adding ECMP. The IP header can be v4 or v6. So what does it look like to tunnel MPLS segment routing over an IP network? Do I have to stand here? I'll have to point at the things.
And you can take the mic out of the.
Oh, okay.
No, he's talking about the pink box.
Oh, the pink box. Yeah. Well, yes, you're supposed to stand there so you stay on the camera.
Oh, so is there a pointer in this as well? Anyway, all right, I'll try and explain. Sorry? Oh, that one, okay. Yeah, this is not one of Luca's super powerful lasers. Right, so what we want to do is we want to get the packet from A to B, but it turns out that the red routers B, D, and F do not speak MPLS, but they do speak IP. So clearly we start by tunneling through B to E. And this is the IP address here, the IP header here. The IP header gets us from A to E directly. Then we have a label that says the next hop is G in the MPLS layer, and a label that says the next hop is H in the MPLS layer, and then we have the packet. So we got the packet to here on its native first hop native IP header. We look at the packet there, and that says, I need to get to G. So we put the IP address header on to get to G. The net result is we carry label H to G, and then G sends it as IP straight across D to H. So that's pretty straightforward. We explained that in previous IETFs. Here's a bit of detail. There is a bunch of detail that you need to go through, but for the purpose of explaining it, I think that we could find no showstoppers, and I think you can trust the authors to work on the detail at another stage. So what about building a service function chain? There are actually a number of ways of doing this. I've got two here, and there is a third one which I'll briefly discuss. So this looks remarkably similar, doesn't it? So what we want to do is to get the packet from A to H via service functions in E, G, and H. So we start off by tunneling the packet from A to E in IP. When it gets there, we get this label L of E, or E of L rather, which says execute service function E. So providing this guy here can recognize the semantics, which you'd assume it could do, it can send the packet out to a service function, or it can execute the service function itself. The really interesting thing is that this looks remarkably similar, top and bottom, to the picture we previously showed. In fact, it is pretty well identical. So let's look at some detail. Again, we've previously described this. There is a bunch of detail. We'll work through the detail if people think this is a thing that's worth pursuing. Conceptually simple. It's important to note that we didn't actually need to turn any major MPLS functions on to achieve this. We just needed to teach each of the critical nodes what the semantics of the 20 bits were. You can have multiple service functions served by the same node. You just need to put some extra, put the right labels in. So if it's going to do 2 functions, you'd put 2 labels in. If it was going to do just one, you'd do one, and not every packet has to go through the same service functions. And what this requires is the mapping of the service function to a 20-bit label and the service function host address. We can put a more complex service function chain. This has multiple multiple functions executed at E, just to illustrate the point. And you do that by putting the labels in the stack. In this example, the host identity is explicitly encoded as a label. So we'd be reusing the concept that segment routing introduced of nodal labels. But nodal labels are sent around in the IGP. So we didn't need to turn any MPLS functions on to do this. Yeah, so there's, again, a lot of detail, but I think the principle should be clear to everyone. So what about in getting segment routing to work in legacy v4 networks or in v6 networks? This looks by now to be a remarkably similar picture. If 20-bit SIDs are good enough for most applications in MPLS, 20-bit SIDs are probably good enough for most applications in an IP network. So with this structure here, which is a structure we've met before, the function of the labels, which are just 20-bit identifiers as to where the packet is to go, conveniently carried in an MPLS carrier, allow us to get the packet from A to H via key nodes E and G, using hardware that is already deployed through most of the world. Chipsets can already do most of this. And we don't need to have the discussion about extension headers, etc. This kind of just works. The encapsulations are already defined. 4023 and 7510 describe how to get MPLS over IP or how to get MPLS over UDP. The number of bits it takes to encode a SID in the packet is, well, it's actually 32, of course, but 20 is the key number. The compact format means that the headers are much, much shorter than they would otherwise be. Again, we do not need to turn on the mainstream MPLS control functions to make this work. We are using the IGP to carry the SID information around in exactly the same way. It can be deployed as an interim until full-featured SRv6 is available in that part of the network. And of course, in networks which are still using IPv4, they will just work with this. Again, a bunch of detail to work through, but no showstoppers as far as I can see. So, conclusion, a single compact data format can support the interconnection of disjoint MPLS segment routing islands, something that we know we need to do. We can also support service function chaining. We can also support IP agnostic segment routing over IP. It's important to focus on the 20-bit instructions, not the packaging in RFC 3032 format. This is just a way of getting a hardware convenient way of getting this to work. And finally, the unification approach has benefits that we think are worth further study. So are there any questions? I guess there probably are from the two at the back of the room.
Ron Bonica, Juniper Networks. First, an observation. Let's assume for a minute that at the bottom of your stack is an IPv6 header.
Yep.
What you have in your segment routing MPLS label stack carries the exact same information as an SRH and SRv6. What's elegant, so it's exactly the same information, it will give you exactly the same functionality.
Yep.
What's elegant is it's much more complex, not complex, compact.
Yes.
32 bits as opposed to 128.
Yes.
And you can reuse all that SR-MPLS technology. So there's something very elegant here.
Thank you.
Yeah, and for those who want to do funky things at the end of an SRv6 tunnel and address frames of a movie or whatever application they have where they might run out of labels, there's nothing that says that at the very bottom behind that last IP header there can't be a whole SR route object.
And indeed, there's nothing to say we can't use a set of labels, one that says what the movie is, one that says what the studio is, and one that says what the frame number is.
Yes, but for those who want to
Yes,
keep along on what they're thinking about, then there's nothing stopping them.
exactly.
So I want to echo what Ron just said, Kiriti compiler. You did have a bullet that said this could be used as an interim solution until a full-featured SRv6.
Indeed.
The only thing that I see missing is that in SRv6, you actually have, at the end, when you get to the destination, you know how you got there. And here, because it's labels, you pop them. Other than that, is there any feature that's missing?
No, I mean, so I've got two points to make about that. If it really is important to you to know the path, you could always stick this as metadata under the label stack. Yes, in fact, it might be interesting to stick the reverse path as metadata under the label stack. Secondly, I kind of take the view that if this is good enough for MPLS segment routing, it's probably good enough for a lot of applications where you're in an IP fabric. No one has complained that losing the label stack was a problem in conventional conventional MPLS segment routing.
They have, but ignore them. So why do you say this interim? Why not just say this is a replacement for SRv6?
Because I don't want that fight.
Hey, I'm pushing you into the fight.
Ahmed Bashandi, Cisco Systems. If we do this, then I assume that MPLS runs everywhere. Well, my phone doesn't run MPLS, my laptop doesn't run MPLS, my router at home doesn't run MPLS. And since you don't want to get into this fight, I don't want to get into it.
Well, hang on a second. Let's understand what we're saying here. I'm using a 20-bit representation of some key points or key instructions in the network. The point I was making was you shouldn't think of this as MPLS. You should think of MPLS as a network programming language. That's what it's always been. And you can still get from your phone through the network because the outer is IPv6 or IPv4.
Okay, let me rephrase. My phone doesn't run 20 bits identifiers. It runs 128 bits or 32 bits.
We will find out. Adrian.
Adrian Farrell, I'd just like to restate what you said. So your phone doesn't run segment routing. So, no, I mean, it may run IPv6. It does not run segment routing. And this is just another way of encoding the segment routing stack. It's not different. It'll still do everything that your phone does already without changing your phone.
No one would associate your address with a label. They just simply put your address down at the bottom of this thing.
Yeah.
Again, if I want to encode functions that my phone wants to do, my phone understands 128 bits. It runs 128 bits. It doesn't run 20 bits.
Well, wait a minute. If we're talking about functions, then it doesn't understand those unless you teach it about them. And you can teach it about a 20-bit identifier just as easily as you could a 128-bit identifier.
But you don't need to go down that hole. You don't need to go down that hole.
That's not true because it already runs the 128. I have to go and modify the kernel, modify tons of things in my phone to understand 20 bits.
I think you need to read the draft. The draft says you put 128 bits on the outside. So the thing that goes to your phone does not need to do the 20 bits.
What is in the draft, it says, or what the command says, that I can replace the 128 bits with 20 bits. And what I'm saying, that's not true.
And I agree with you. It's not true. That's not what the draft says.
Actually, the draft, I think I should explain. The draft, which was written in quite a hurry, is not quite such a complete story as the slides. So if you see a difference between the draft and the slides, believe the slides, and the draft, the next time you see it, will be a much better representation of the story.
Yes. Ron Bonica, Juniper. Right now, we don't need to argue SRv6 versus what you're proposing, because that's not the discussion we're having today.
Yes.
We're just arguing what you're proposing, and that seems to be pretty good. Everybody seems to be liking that.
Right. So we'll produce a 0-1 that expands.
It'll hopefully be a whole lot better than the 0-0 because I had to read it twice, and having had some previous conversations with one of the authors, I got it, but it's.
We will do a much better job next time. We apologize for the omissions in the original version. Okay.
Okay.
Thank you.
So, Shen, are you ready to prepare now, present now? Oh. Yeah. Yimin, are you prepared to present at this point in time? Yeah, you need to get yourself in the queue if you want to speak. Well, he seems to be on your line, but I'm not getting anything, so Carmen, come on back up. Cameron, sorry.
Yeah, hello everyone. My name is Karman. This is just a quick update to a Yang data model for LDP from last IETF. So a little bit of history about the revision. We originally had one single draft that covered that Yang data model for both LDP and MLDP. And that draft was getting way too big. And based on our recommendation from the working group and the chairs, we split that draft into two different IETF working group document, one for LDP and one for MLDP. So I'm presenting this update just for LDP, and later on the Friday session, there will be a update for MLDP draft on the Yang model for MLDP draft. So we posted, we split the document right after IETF 97. And since then, we have posted another revision of the LDP document and MLDP document, which basically takes care of one major comment from Mpls RT review, which was to basically consider splitting modules, LDP and MLDP modules into the respective base and extended features, meaning that our model was way too big, even for a given area for LDP and MLDP. So we were asked to look at the division about base and extended models. So revision 01 is basically a revision that takes care of LDP partitioning of the features between base and extended. And this was posted right before this IETF. So changes in this revision 1 is basically partition or LDP feature set or our configuration and state model and other stuff into base and extended parts. We're the team that has been working on this LDP and MLDP Yang activity. We met a few times and partition and categorize features accordingly. The base category basically includes all those features, most of the features which are already specified in LDP base RFC 5036. It does not cover everything from that RFC, but all the base features. So one of the kind of criteria and rule that we use to categorize base features are, those are the features which are required for any minimal LDP deployment. For example, without LDP LSR ID, you can't really, that feature is almost undeployable. Versus, LDP IGP sync feature, that's not really a base feature. That is a good feature to have, but that's probably goes into extended category. So that was a criteria we used to categorize base versus extended. So anything that didn't fall under base, of course, went into extended model. So there are a couple of slides on different feature partitioning. We can go through this. You can go through this later. One thing I wanted to highlight is that since we also have LDP IPv6 RFC, the team agreed and decided that V6 LDP will not be part of base. It's a base module. It will be extended module. That doesn't mean that we don't have to support LDP IPv6, but the base deployments which are already out there really do not have LDP v6 because it's very recent. So anything about v6 is in the extended model. Any bells and whistles which are not really for primary use for LDP are in the extended model. So you can see that in the base model there's only a few ticks here. Same on the next one, and same when for the peers, there are lots of things that you can configure under LDP peer. There's the password you can tune, you can have the capabilities, but we all those per peer tuning are part of our extended model. So in order to achieve that, so our existing Yang module was IETF-MPLS-LDP. Now it has been broken into two separate modules. One is a base model, and other is extended module. It is important to know that in the base module, everything is mandatory. So there's no if features support in the base model. And in the extended model, which we call LDP-EXT, prefixed by LDP-EXT, it's optional for implementation, and there are other IF features which are part of that module. Right. So the base LDP base model is still augments our control plane protocols and the routing. However, our extended module now, which we call IETF Mpls LDP extended, that augments base LDP model. So that's just Yang logistics. So if you can see now, I mean, I didn't have enough place to put everything, but for the extended, for the base config, so this is how the hierarchy now looks like. It's very simple. Only things is keeping in LDP is basically a couple of things under address family enablement, a couple of things on discovery interfaces targeted. These are all base features for LDP, and a couple of things under peer. All other bells and whistles have moved to extended model. So really in the Yang, if you generate a tree from base model, this is what you will see. If you generate the whole tree with base and extended, probably you'll see it's 3 times the size of the tree than what I'm showing here. So again, for the extended, I just put for the sake of comparison to base. Again, it doesn't cover everything, but you can see this almost at least double the size of the base model that we have in LDP. So we have a couple of open items that team has been discussing, haven't been able to conclude one way or the other, and would like to get working group or consensus or input on this. Our model, original model that we started, defined label policies for label allocation, inbound filtering, outbound filtering, all these kind of policies at different levels. For example, you can have a policy at the global level, meaning that it's a one policy that kind of takes care of both V4 and IPv6 address family, or you can policies per address family. Even we have a policy per peer, which applies to per peer policies for every address family under that peer, or a policy per peer per address family. So policies are on a very levels. So we haven't decided one way or the other, which policy should really make it to base, and the remaining should go to extended. So this is one open item. I would like to get your feedback, maybe here or the mailing list, and then I think we can move forward. For now, if I remember correctly, we decided to keep per address family as in our base model. So there are a few pending items that we haven't completed on the draft. We still have to specify some default values and have to realign our draft with respect to intended and applied config changes that we still have to make. But I think our major focus from a couple of ITFs to this ITF was to split LDP and MLDP, and within each LDP and MLDP split base and extended. So next step for this draft is basically address these pending open items and try to get this draft ready for working group last call. We are hoping to get it ready before next ITF, but it all depends how much rework we have to do with our draft if we get any input from the working group. Okay. So any questions?
Thank you. Before we go on to the next presentation, the one document that's been in the queue for half a year, what happened was the expert reviewer took a long time, but finally reviewed it, but the author missed the email message that said it was done after all that time. And so it sat a couple of more months, and then Loa recognized it and they worked through the details, and Deborah has promised to review it quickly, and we'll get it moving along, hopefully within the next week.
Yes.
So Yamin, you're ready? Yeah. Okay, you're on.
Can you hear me?
I can hear you.
Okay, great. So this is the Mpls.
I hope he's not sitting there presenting.
Try it again, press it only once, and then leave it as it is.
Oh, you're
Okay,
on.
okay. So next slides, please. All right, so egress protection. Hello, can you hear me?
Yes, yeah.
Okay, sorry about that. So egress protection is essentially the fast reroute for egress failures, which include egress node failure and egress link failure. Egress protection is equivalent to the traditional fast reroute for transit node and link failures. Fast reroute is desirable, mainly due to local failure detection and local repair, which can provide very fast traffic restoration and complement global repair and network convergence. Next slide, please. Egress failures are a little bit complicated than the traditional transit link and node failures. In the case of egress link failure, is a failure at the service level. In the case of egress node failure, it's a failure at both the service level and transport tunnel level. Therefore, egress protection must be a two-level protection. That's why in this draft, we introduce the notion of a protector and the notion of protection service instances on protector. Next slide, please. This draft provides a generic and unified solution for egress protection. It's a multi-transport and a multi-service solution, meaning that the solution works with all types of transport tunnels and all types of services. It's also considered as a framework because it provides some guidelines towards the services. Any service, if it follows the guidelines, can be easily supported by the solution. A given type of service may need some protocol extensions. In this case, you would need to write a extension document. One example would be the pseudo-wire egress protection, which is covered by RC 8401. A given service may not need any protocol extension. In that case, you may need to write a informational document to describe how it works. In the case of layer 3 VPN egress protection, we actually described it in the current draft as an example. Next slide, please. There are some secondary goals of the draft, such as support for P2MP and P2P tunnels, and some requirements from the perspective of PRR and protector. So I will not get into the detail in this presentation. So next slide, please. The main building blocks of the egress protection include the router at PRR, protector, transport tunnel, context ID, and context-based forwarding. Next slide, please. So the current draft is version 4. Version 2 was presented last year in Berlin. Since then, we've got two new co-authors to help us improve the quality of the draft and move the draft forward. Next slide. So by default, the draft should work with all existing vanilla, tunnel protocols. However, we modify the text to not to preclude any tunnel protocol extensions, if these extensions can facilitate egress protection establishment. So one example would be the RSVP egress protection draft. Next slide, please. We added a section for on egress link protection. So in this case, the protected egress will act as a PR. Next slide, please. We also add a section on the centralized protector model. In this case, there will be a single or a small number of dedicated protectors to protect all the egress router and the egress links. So this model has an advantage in scalability than the other model, which is called a co-located protector model. So I think that we believe at this stage the draft is mature, and therefore we like to request for working group adoption.
So how many have read this draft? And how many believe this is something that we should be working on? And how many believe that this is a sound basis to adopt as a work group document on this? A little bit less, but so we will take this to the list.
All right, thank you.
Any questions? Okay, thank you.
Thank you.
Yeah.
Yeah, so that.
Hi, my name is Tarek Saad from Cisco. I am presenting an update on this draft about RSVPTE summary of fast reroute extensions. We had a new co-author join as part of this update, Rakesh Gandhi. So I plan to give a refresh background and update, and then close with the next steps. So this draft was initially presented back in IETF 92 in Dallas, and then we did subsequent updates in following IETF's meetings. The focus is on addressing a scalability problem with RSVPT FRR. As defined in RFC 4090. The solution tries to minimize the amount of signaling and processing overhead that happens between the PLR and merge point after a failure. So it does so by associating the primary LSPs with the bypass protecting them, and by exchanging the summary refresh message ID before the failure, so that summary refreshes continue on after the failure. This document was reviewed by Lou Berger, and he provided comments, and we addressed those. It was also reviewed by the Mpls review team, and we addressed the comments coming from them. And finally, the Shepherd, document Shepherd, also provided us comments and we addressed them. In essence, this draft is proposing an extension to the association, RSVP association object by introducing a new association type for bypass summary FRR. It does contain the identity of the bypass and the bypass group identifier and the summary summary refresh message ID. The second object that this draft is trying to introduce is a bypass FRR object. Basically, it's carried in the bypass LSP session path message, and it contains all the bypass group identifiers that have gone active after the failure. So we are defining FRR active C-type as part of that object. So in terms of next steps, we think this document is stable enough, and we welcome further comments, and we ask for working group adoption.
So how many have read the draft? And how many believe this is something we should be working on? And how many believe this is a sound beginning for that work? Okay, thank you. We will take that to the list.
Thank you. Any other questions?
Okay. So we're finishing early today, but we have a rather packed agenda. Oh, somebody have a question? Oh. Just blue sheets. So we're done for today. Friday we have a very packed agenda. So see you all on Friday.
Finally worked.
Yeah. Intimidated by a red button that you have to.
I think you took it only once or something like that.
Yeah.
And then.
You know, this is always the kind of button they show for
Yeah, I know.
launching missiles.
Yes.
Who has the other blue sheet? Hmm?